Okay, so obviously I'm not ChatGPT. It's actually mind-blowing that I even feel the need to clarify this, though. How in the world did a model made from linear algebra manage to pass as a human? Let's build a mathematical model of language. The first step is to divide text into pieces called tokens. The way this is done varies, and we'll use words. To process these tokens, we can represent each one as a vector, a long list of numbers, which we'll call its embedding vector. An embedding can be visualized as an arrow that points in a direction and has a certain length. We want the direction of that arrow to correlate to the word's meaning, and the length to represent the intensity of its meaning. Words have more than one possible meaning, but we're converting each word into a single embedding vector. We can fix this by adding a way to capture contextual information to our model. Let's use a matrix, which can capture any kind of contextual relationship for this. By applying a matrix as a transform to an embedding vector A, we get a delta vector, delta E, which we can then add to a second embedding vector B to change its meaning. Not all tokens are actually related to each other, though. Our model needs to reflect that, so let's add two more matrices, one for A and one for B. By applying the matrices as a transform, we can map A and B to a pair of result vectors, which will be more aligned when A and B are more closely related. Now, we can scale the length of delta E by how related A and B are before adding it to B. However, so far, we've just been assuming that we can find some matrices with numbers that produce our desired behavior. We can't poof these out of thin air, so we have to search for the best ones by feeding our model lots of data. Language models run this process many times with different matrices in a process called attention and collect the delta vectors together to apply them once all the computations are done. The final goal is capturing all the different possible contextual relationships and distilling, theoretically, 100% of the meaning of the entire chunk of text into a single vector. Once we've got that, we need one final matrix to get a probability distribution predicting the next token. We can then apply the model repeatedly with some randomness to generatively complete text. To turn this into a chatbot, just format the conversation like an act from a play and auto-complete the lines for the assistant's part. It turns out that predicting what someone might say with linear algebra is extremely effective. Enough to change the world.